Hello everyone, I'm Yao Li from Chang'an University. In this lecture, we are going to learn some basic knowledge about one of the mostly used geotechnical tests, direct shear test. Before learning the details of the test, we need to be clear about the testing conditions. Loading of the soil generates excess pore water pressure. In tests, two extreme cases are generally considered, which are tests in drained and undrained conditions. Drained condition is usually to test the soil considering its long-term condition behavior. In a drained condition, the excess pore water pressure developed during loading on soil dissipates, and the volume decreases. As a result, there is no excess pore water pressure during a test. Drained condition is usually used on cohesionless soils with high permeability, and tests with slow loading rates. Undrained condition is usually used to test the soil considering its short-term condition behavior. In an undrained condition, the excess pore water pressure developed during loading on a soil cannot dissipate, and the volume is constant. As a result, there is excess pore water pressure during a test. Undrained condition is usually used on cohesive soils with low permeability, and test with fast loading rate. It should be noted that in reality, neither condition is true. They are limiting conditions that set up the bounds within which the true conditions lies. This figure shows the direct shear testing practice. The soil specimen may be square or circular. In direct shear test, shear speed is used to control the drainage condition. In drained condition, a slower shear speed is used. In undrained condition, a faster shear speed is used. In the first figure, we can see the top half of the box is fixed in the x direction, where a vertical load is applied on the top surface. The yellow part in the middle is a tested soil. In the second figure, the bottom half moves in the x direction, where the top half is fixed. Depending on the equipment, the shear test can be either stress-controlled or strain-controlled. In strain-controlled tests, a constant rate of shear displacement is applied to the bottom half of the box by a motor. The constant rate of shear displacement is measured by horizontal dial gauge. The resisting shear force of the soil corresponding to any shear displacement can be measured by a horizontal proving ring or load cell. The shear stress can be calculated by dividing the measured shear force by area A. Area A is the horizontal cross-section area of the soil specimen. The volume change of the specimen during the test is obtained in a vertical dial gauge. The two figures show the deformation of the soil specimen during a direct shear test. When the bottom half moves to the left, the top half is stationary. As a result, the middle plane that connects the top and the bottom half forms a slip or failure plane as the bottom half moves. A possible failure zone is gradually developed near the failure plane. When the material's shear strength is exceeded, the specimen fails. There are two important values in a direct shear test, sigma and tau. Sigma is the normal stress applied on the top of the specimen. Tau is the shear stress measured during a test. On the different normal stresses, the measured shear strength is different. For loose sand, normally consolidated clay or clay with OCR equal or smaller than 2, we can get following results from a series of direct shear tests. In the figures, delta V is the change of volume during test. Delta H is the increment of the shear displacement. Sigma 1, sigma 2, sigma 3 are different normal stresses in different direct shear tests. As mentioned in the last slide, on the different normal stresses, the measured shear strength is different. So we can see three different curves in the first figure. The horizontal axis of the first figure is the increment of the shear displacement. Top of the y-axis is the shear stress, and the bottom of the y-axis is the change of the volume. It can be seen that with the continuous increasement of the shear displacement, the shear stress of tested material increases to a relatively stable state is reached. Similarly, the volume are continuously decreased to a relatively stable state is reached. In the second figure, results from the same test are presented. The horizontal axis of the second figure is applied normal stress. Y-axis is the shear stress in tests with different normal stresses. Corresponding peak shear stress is recorded, indicated by a star in the second figure. When the tests are repeated many times, by fitting the points we can find the linear relation between normal stress and shear stress, then the friction angle at peak shear stress can be determined. For dense sand and clay with OCR greater than 2, similar figures can be obtained. In the first figure, the shear stress increases first and reaches the peak value, then it decreases to critical state. The volume decreases first and then increases. During shear, we can generally see two kinds of shear behavior: shearing contraction and shearing expansion. Shearing expansion is a shear behavior showed increasing volume under increasing shear displacement. It can be seen that the tested soil showed shearing contraction first, followed by shearing expansion. For clay with OCR greater than 2, we can get the linear relation between normal stress and shear stress, its cohesion and friction angle at peak shear stress. For dense sand, we can get the linear relationship between normal stress and shear stress, and friction angle at peak shear stress. This table shows the ranges of friction angles for different types of soils. The friction angles, including friction angles at peak shear stress and friction angles at critical state. It can be seen that the friction angles at peak shear stress is greater than that at critical state. Generally, the direct shear test is an inexpensive, fast, and simple method to determine the friction angles and cohesion, but it has some shortcomings. For example, the tested specimen is forced to shear along a predetermined plane, which is fixed at the middle of the specimen. Stress distribution along the failure plane is non-uniform, and there is stress singularities at the edges. The rotation of principal stresses cannot be controlled. The actual failure plane is not a plane. One cannot control the excess pore water pressure. Here are all the contents in this lecture. Thanks for your listening and see you next time.